will continue the discussion with transient and absorbing probabilities, that is your reducible Markov chains. So, now here for example, look at this transition diagram. So, there are 4 states and you see that from 1 you can either come back to 1 or go to 3, but then 3 once you reach 3, then the probability of returning to itself is 1. So, therefore, this is a certain event. So, once the process from 1 goes to 3, the process will stop there. Similarly, from 1 it can go to 2, and then from 2 if it transitions to finally to 4, then 4 is an absorbing state, and so your process will again stop here, right. And similarly 2. So, you can see that from 2 also you can go to 1 and 3 or 2 to itself and then 2 to 4. So, 1 and 2 no, I saw 1 and 2, this should be 1 and 2. 1 and 2 are transient and 3 and 4 are absorbing, right. That you can immediately see just by looking at the transition diagram, that once, and of course, you can see that over a short period 1 and 2 will be visited, right, because they are transient. So, for a while the process may go from 1 to 1 itself, or from 1 to 2, then 2 to 1, that may go on for a while, or 2 to 2, but then the moment it the process transitions to either 3 or 4, it stops, right. So, therefore, for over a short period of time 1 and 2 will be visited, but ultimately the process will either enter state 3 or 4 and then stay there. So, the process will end. Okay. And so, now using this I want to talk about absorbing probabilities. So, for example, the questions that arise. So, I have just first written the first question, even though this is plural, we will talk about the other question after this. So, which absorbing state will be entered? Of course, here again we will only talk in terms of probabilities, which absorbing state or what is the probability. Now, just to point out the difference between the absorbing probabilities and the steady state probabilities, you see. Now, just look at this example. So, okay, what I am saying is that we will answer this question by computing absorbing probabilities. And so, before I start talking about the method for computing the absorbing probabilities, let me just give you a feeling what we are talking about. See here, if you are in state 1, then the probability of transitioning to 3 seems higher than transitioning to 4, because well, okay, you might say that the one, of course, if it happens in one step, then this probability is half, or then it can happen that you can go to itself and then transition. So, that will be also, then that will be so this will be half plus half into 1 by 4. So, let us just compute this in 2 steps, and then if you so transitioning, if you start in 1, then transitioning to 3, let us say in 2 steps. So, half plus half into 1 by 4, but if you are in 2, so computing the transitioning, if you transition from 2 to 3, we cannot do it in one step. So, the 2 step transition probability will be, so the path will be from 2 to 1, from 2 to 1 and then 1 to 3, and so this would be 2 to 1 is 1 by 3 and 1 to 3 is half. So, 1 by 3 into half will be 1 by 6. So, this is the probability, 2 step transition probability of going from 2 to 3. Fine. I mean again the example that I am trying to take is, so half plus half into 1 by 4 will be how much? This will be 1 by 2 plus 1 by 8, which comes out to be 5 by 8, right. You are connected to 3 from 1 directly. So, this is what we will try to bring out through the computation of the absorbing probabilities, that it looks like that transitioning from 1 to 3, the probability would be higher if you are in state 1, and if you are in state 2, then the probability should come out to be lower than that. So, in other words, what we are trying to make a case for is that the absorbing probabilities are not independent of the starting probabilities, that means the starting state, whereas steady state probabilities we saw So, unlike steady state probabilities for an ergodic process, the absorbing probabilities depend on the starting state. See, steady states were independent of where the system started, okay, and therefore, we could compute simply pi equal to pi p, and it did not matter where the system was, because remember all the rows of the matrix became identical, right. But in the absorbing probabilities, it will depend on where you are starting, and this is what we want to make sure. Like, okay, this will now we will ultimately, when we compute the probabilities, we will show that the absorbing probability when you are in state 1 to 3 is higher than when you are in state 2, and similarly for 4 it will be higher when you are in 2 than when you are in 1. So, we will show, because here we will have to then let us say I take 3 steps, 4 steps, 4 transitions, then I can show you that the numbers here when you in state 1 transitioning to 3 will be will have a higher value than transitioning from 2 to 3. So, let us see, it will come out. So, let me make these definitions. Aij is the probability of reaching the absorbing state j from state I, where I is a transient state. Okay. We want to compute this. Now, of course, one way is that you can use the first passage probabilities. So, Fij, so that means for the first time you transition from I to j in n steps, and then you sum this up from n 1 to infinity. Now, this is not computationally efficient, right, because we will have to compute all the higher powers of the transition matrix, and then we want to compute the Fijn's. So, an alternate method, and this should look familiar, because we have already used this kind of argument. So, now what we are saying is that if you want to compute Aij, then the transition either takes place in one step, that means in that case the probability is Pij. So, this is the probability of transitioning from the transient state I to the absorbing state j. So, then this is Pij plus, or I transition from I to another transient state k. So, that probability will be Pik, and then Akj will be the ultimately transitioning from the transient state k to the absorbing state j. So, this will be this number with this probability, and this is the probability of transitioning in one step from I to j. So, this is the argument, right. Now, a complete set of linearly independent equations will be obtained if the same argument is applied to each transient state. So, that means here I have done it for I. So, whatever the number of transient states, from each of them I will try to find out this probability of transitioning to the absorbing state j, right. And then I will have a complete set of linearly independent equations, and we will then solve for the Aij's, and then we will get the so we will be able to answer the question that which absorbing state will be entered, in the sense that you will say that a particular absorbing state will be entered with this much probability starting from this state. So, this is the way we will be able to answer that question, right. So, now let us just take the transition diagram. So, we are considering this process, and if you write out the equations, then you see from one transition state 1 you want to go to absorbing state 3, then if you write out these equations, it will be P13. Either you do it in one step, or you go to the transient state 2 P12 and then A23, or you come back follow the loop P11 into A13. So, this is your equation when you want to write down for A13. Similarly, you can write it down for A23. So, this will be P23 plus P22 A23, right. From 2 you can either transition to 3 in one step, P23 or P23 in our case will be 0, right, or you will have to go from 2 to 2 loop, and again A23 there will be A23. So, you come back to itself, and then A23 the probability of transition from 2 to 3, then or you go from 2 to 1, and then you go to from 1 to 3. So, these are the two equations. Now, if you substitute for the Pij's, we obtain these two equations, right, and you can see that here the variables are A13 and A23, right, because this is 0 as I said. P to 3, there is no arc from 2 to 3. So, you have 2 unknowns and 2 equations. So, we should be able to solve for A13 and A23 here, right. Okay. So, see, if you look at these equations from here, if you bring A13 here, it will be 3 by 4 A13 equal to half plus 1 by 4 A23, and here because this is 0. So, you bring A23 here. So, this will be 2 by 3 A23, which is equal to 1 by 3 A13. So, that immediately gives you 2 by 3 A23 equal to 1 by 3 A13 gives you A23 is half A13, and now if I substitute for A23 in terms of A13 in the second equation, which was 3 by 4 A13 is equal to half plus 1 by 4 into 1 by 2 A13, right. So, then I get the equation for the value of A13, which is 3 by 4 minus 1 by 8 A13 is half, that is 5 by 8 A13 is half. So, therefore, I get the value of A13 as 4 by 5. So, once my A13 is known as 4 by 5, I can compute A23. So, even from here only one could have concluded what I was trying to show you, but of course, it would have needed at least 2 to 3 computations of 3 or 4 paths to get you to this, that A23 would be half less than A13. The probability of reaching the absorbing state 3 from 2 is smaller than the probability of reaching 3 from 1. And maybe you can say that the intuitive feeling looking at the diagram, because you have a direct connection here and here you will need at least 2 transitions to come here. So, therefore, this was the feeling which you can now sort of validate by doing these computations. So, therefore, A23 comes out to be 2 by 5, which is less than 4 by 5, and therefore, it is less than A13. Now, certainly A13 plus A23 will not be equal to 1, because we are not sure whether we will be So, A13 plus A23, yes, because we do not know whether we will from 1 we will definitely reach the absorbing state 3, you may also reach the absorbing state 4. So, therefore, these two probabilities will not add up to 1, not necessarily. Okay. But if you fix the initial state, then the system will enter one of the absorbing states. If you fix the initial state, that means if I simply say that my system is in state 1, then of course, A13 plus A14 will have to be 1, or if my system is known to be in state 2, then I must transition to either 3 or 4 ultimately. So, therefore, A23 plus A24 will have to be 1, right. So, if you know this, then I can immediately compute, because I have already computed A13 and A23. So, then A14 will be 1 by 5 and A24 will be 3 by 5, right. And so, here again the same thing gets validated, that your A14 is less than A24. So, the probability of transitioning from 2 to 4 is higher than transitioning to 4 from 1. Let me just make this 1. Okay. This is the whole idea, right. Now, A14 and A24 I could have also obtained just as I wrote down the equations for A13 and A23. So, the same way I would write down the equations for A14 and A24 and I would compute them, right. Okay. So, this is what now this is the method for computing the absorbing probabilities, and as we have seen that these probabilities will depend on where the system is, and unlike the steady state probabilities which are independent of the starting state. Okay. Now, let us just generalize this process. If I now call the A as the matrix of these transition probabilities, then here your I will vary, I mean transition probabilities from transient states to absorbing states, then I will be the rows of the matrix are the these vary over the transient states, and J varies over the absorbing states, right. So, the columns correspond to the absorbing states and this. So, for example, in this case it is 2 by 2. So, in this case your matrix will be 2 by 2, and you can see that if I wrote down the equations for A14 and A24 also, then I will have a matrix here corresponding to all these absorbing probabilities that I want to compute. So, then in that case the system could have been written as the matrix A, and this will consist of, remember the R is the matrix consisting of transitioning from a transient state to absorbing state in one step you are writing. So, Pij's. So, these were, so therefore, R is a sub matrix of your transition matrix P, which has the same dimension as A, and the rows of course correspond to the transient states and the columns correspond to J, because you are transitioning from transient state to absorbing state in one step. So, therefore, R is exactly the sub matrix of P of the same dimensions as A, right. Then we wrote down Q A. So, remember this was the this will consist of the transition probabilities from a transient state to another transient state, because we were writing. So, either from I to j you did in one step, then those probabilities are here, or you went from I to k, another transient state, and then from k you went to j finally. Okay. So, I to k, this is transitioning from a transient state I to a transient state j k. So, Q will be that matrix, right, and since the columns here are transient states. So, and the rows of A are transient states. So, this matches. So, this is compatible, and this will be your system of linear equations written in a matrix form when you want to compute the absorbing state probabilities, right. Okay. And so, so let us see. So, here for example, if you bring to this side, it will be I minus q times A equal to R. So, we continue with the computation of through this matrix. We will, and we will look at the entries of what do we mean by. So, in other words, it will be I minus q A is R. So, A will be I minus q inverse R, and I minus q inverse will exist. Okay. So, I minus q A is R. So, this implies that A is I minus q inverse R, right. So, you see here A represents the probabilities of reaching an absorbing state from a transient state, and so when we set up this equation, a valid one, then there must be a solution to this system. So, that is what we are saying. So, therefore, I minus q, and it is a unique solution. So, therefore, I minus q inverse exists, that is what we are trying to say. So, I am giving the argument in this way. Normally, you try to first show analytically that the matrix is non-singular and hence the solution exists, but here we know that the system will ultimately settle down into one of the absorbing states. So, these probabilities are finite, and therefore, the solution exists, and hence I minus q must be invertible. So, this is the whole idea. So, the star's equation has a solution, has a unique solution. So, I minus q inverse must exist. And now, we have interesting interpretations of the elements of I minus q inverse also, and as I said, the questions that keep arising, we will go on answering them, and in between we will also look at the interpretation of the elements of I minus q inverse. So, the second question that arises is how many times a transient state will be occupied before absorption occurs. So, now the second question is how many times will a transient state will be occupied before absorption occurs, because obviously, this is you are talking of a reducible Markov chain, and so you want to know how many transitions on the average will go continue before absorption occurs and the system stops. So, this is the question mark, right. And so, for each particular transient state, we want to ask this question. So, and surely this is a random variable depending on the starting state, right. How many times transient state will be occupied again is a random variable, and it will depend on what is the starting state, right. So, let us define Eij as the mean number of times that transient state j is occupied, given that initial state is I. So, remember again computing your Mij's, which was your mean time for transition from I to j in the ergodic case. Then we also talked about the same thing while computing your Fij's, and now and then the absorbing states, the probabilities of going from a transient to a absorbing state Aij's. We were using the same argument which we will use here again to compute, to write down the equations relating these various Eij's, which are mean number of times that a transient state j is occupied, given that the initial state is I. So, here this is of course transient state, I is a transient state again. So, I to j. So, when I is not equal to j, then of course, you will go to I to k and then k to j. So, this will be the mean number of transitions that you need for transition from k to j, and this is the probability of transitioning in one step to I to k when I is not j, and this summation will be over all transient k's, right. So, this is one set of equations. The other would be if I is equal to j, then you are computing Eii. So, it will be one step you can go from I to I, you transition from in one transition to from I to I. So, therefore, number of transitions is 1, plus you again transition from I to k, where k is transient, and then from k to j. So, the mean number of times. So, the same argument continues, and so in matrix form these equations, because now we have these relations for all I to j, and this is from I to I. So, the same dimension as q. So, the relationship is that E is equal to I plus q e, and so here now your E is actually nothing but I minus q inverse, and this is what I wanted to say, that you can relate the elements of I minus q inverse and give them a meaning. And let us just look at the entries of I minus q inverse for the example that we were discussing, just with 4 states where 2 were transient and 2 were absorbing. So, so in that case your R was half and 0 and 0 1 by 3. This was going from 1 to 1, and this was going from 3 to 3, sorry 2 to 2. 1 and 2 were transient, and 3 and 4 were absorbing, right. And then Q was the matrix of transitioning from transient state to a absorbing state. So, the diagram you can just refer back to the diagram, and so this will be 1 by 4 and 1 by 4. That means, from one transient state you could go to 3 in the probability is 1 by 4, or you could go to sorry, I will just repeat this. Q is basically from transient. So, this is 1 and 2, and this is 1 and 2, I am sorry. So, 3 and 4, maybe I will just again just draw the figure. So, this was 3 and this is 4, yeah. And so, you had this, you had a loop here, then you could come here and you could go there. This was your diagram, sorry. So, I should have been careful. Yeah. So, Q is just the matrix consisting of where the rows and the columns both correspond to transient states, right. And so, in this case this loop had probability 1 by 4, and then you could go from 1 to 2 also with probability 1 by 4, and from 2 you could go to itself with 1 by 3, and this was also, and then you could go from 2 to 1 probability 1 by 3, right. Okay. So, you can just verify these numbers. Okay. Now, so I minus q will be this matrix, and therefore, I minus q inverse will be 8 by 5, 3 by 5, 4 by 5 and 1 by 5. We can okay. And then we also computed, we made these computations. So, your matrix A, which is I minus q inverse times R, is this matrix, and this agrees with our calculations that we had done, right, 4 by 5 and 2 by 5. So, we said that this is higher than this, and that this is higher than this, and these computations were all there. Okay. So, that is there, but now let us look at the elements of I minus q inverse. So, look at E 2 1 for example, because this is our matrix E. So, E 2 1 is this, okay, 4 by 5. Now, this is the mean number of times that state 1 will be occupied before absorption occurs, given that the initial state of the system was 2. Okay. So, starting from 2, you want to find out the probability that you would be going on finally going to an absorbing state, and but in the meantime the mean number of times that state 1 will be visited before absorption occurs. So, that is 4 by 5. So, now it will be interesting, you can just take up any physical process that can be modeled as this reducible Markov chain, which has only transient states and absorbing states, and then you can try to give meaning to these numbers, right. And then if you add up now, for example, E1j, where this is mean number of total transitions before absorption occurs, given that the system was initially occupying state 1. So, now you want to compute these mean number of times total transitions before, because remember we computed 2 1 here, then I could have also computed E2 2, right, E2 1, or for example, here if your starting state is 1, then you go to 3 or to 4. So, this is so we said that E2 1 is 4 by 5, which is the mean number of times that state 1 will be occupied before absorption occurs, given that the initial state of the system was 2. So, starting from 2, then I will occupy 1 on the average 4 by 5 times before absorption occurs, right. And similarly, now if you add up EIJs, E1j over j, which is again transient. So, this will give you that means starting from state 1, then both the transient states will be occupied before absorption occurs. So, this will give you, so therefore, for example, when this is 1, then in this example it will be E11 plus E12. So, mean number of times state 1 is occupied or state 2 is occupied, both are transient. So, this total will give you the total transitions before, mean number of total transitions before absorption occurs, given that the system was initially occupying state 1, right. Okay. So, starting from state 1, how many mean number of transitions can occur before absorption occurs, right. So, here this was a particular element which is 2 1, that means starting from 2, how many times will mean number of times 1 will be occupied before absorption occurs. Now, you are saying starting from 1, what is the total number of mean number of transactions or transitions which will occur before absorption occurs. So, it will be E11 plus E12, because either 1 can be occupied or 2 can be occupied before before absorption occurs. So, that will be 11 by 5, and in the case when you are starting from 2, then 2 1 plus E22, that probability is 1. The mean number, again it is not probability, it is the mean number of total transitions. So, when starting from 2, it will be 1, okay, and this number is 11 by 5. So, starting from 2, that means it is faster, the absorption occurs faster, mean number on the average, that is what we are saying, right. So, see the question that we had answered was that when will starting from state 1, which is one of the transient states, how many transitions before absorption occurs. So, therefore, when we are looking at the elements of I minus q inverse, so this is E11 plus E12, because either absorption will occur from state 1 or absorption will occur from state 2, right. So, therefore, you add up the two elements of I minus q inverse, and this comes out to be 11 by 5. Similarly, you can find out if you started from state 2, then how many transitions occur in the average before you go to an absorbing state. So, that sum will be E21 plus E22, and therefore, so that was I thought I will just emphasize again the interpretations of the elements of I minus q inverse. Okay. Now, a different question, this is, suppose you specify an absorbing state, okay, and then you want to know how many transitions will occur before the specified absorbing state is occupied. Okay. So, this is also because that will give you an idea as to how long the process will continue. And because once the absorption occurs, once you occupy an absorbing state, then your process is over, right, or it will just continue to stay in that same situation, okay, same state. So, and of course, this question will arise if there are more than one absorbing states, because otherwise if there is only one absorbing state, then you know that ultimately your process will reach that state and your process will stop or will come to an end. So, if there are more if there is only one absorbing state, the question can be answered by mean first passage time. So, that means you will ask the question that starting in state I, in the transient state I, how many transitions on the average before you reach the state j. J may be any state. So, if there is only one absorbing state, you can find out your mean first passage time f I j, and that will be the answer to your question. But if there are more than one absorbing states, then final transition will occur to only one of them, but you do not know, it is not known to which one of them, and therefore, the mean first passage time can be infinity in this case, because you do not know to which absorbing state you will go. So, and once you reach one absorbing state, the other one will not be visited ever, and therefore, the first mean passage time will go to infinity. So, therefore, here when you have more than one absorbing state, then you need to compute make some computations to be able to answer this question, that how many transitions will occur before the specified absorbing state is occupied, right. So, what we will do is, in that case we will compute the conditional mean first passage time. That means, given that you are in a particular state, then we want to know. So, mean first, given that passage has occurred to an absorbing state, right. So, that is what you are saying here, that you are specifying the absorbing state, and then you are so the mean conditional the conditional mean first passage time is what we need to compute. So, given that you are going to be occupying the absorbing state, let us say j, then you, so here you are defining this mij as the conditional mean passage time, mean first passage time, it should be mean first passage time from I to j. So, let mij denote this number, and this is different from the mij, the mean number of transitions required for going from I to j when you are considering the ergodic process, when all states were recurrent. So, that mij is different from this one. So, here we are saying this is the conditional mean first passage time from I to j. So, you are occupying state I, and you know that, and you want to transition to state j, which is an absorbing state. Okay. So, now here we will write the following equations. So, aij, remember, was the matrix A that we had computed to compute the absorbing probabilities. So, then aij is the probability of transitioning from I to j. I is a transient state, j is a absorbing state, then mij, as we have said, conditional mean first passage time from I to j, right. So, you are occupying state j, then this can occur either in one step. So, 1 into aij, right, and then here it will be you may not transition to j right away. So, you will transition to some k, and pik into akj. So, k will again be a absorbing state. So, you transition to pik into akj mkj. Okay, right. So, therefore, then the transition from k to j, absorbing probability from k to j, and then mkj. So, this will be trying to write down the equations for mij, so that we have a system of equations, and we can solve for these conditional mean first passage times. So, is that okay? So, here this is I to k, that means you may transition from I to another absorbing state, but then in that case, okay, and then no, it has to be, sorry, k is not, k cannot be an absorbing state, right, because you see you can immediately see that the argument is not correct, because if you are from I to k, then you cannot transition from k to j, because once you are in absorbing state, then it is done. So, k is a transient state. So, you are transitioning from I to k. So, I is a transient state, k is a transient state, and then you are finding out the absorbing probability of going to j, and mkj will be the mean first passage time, right, conditional mean first passage time. That means, you want to go to j when you are in k. Okay. So, m k j into a k j into p I k. So, this you sum up where k is. So, I should not say that k is not equal to I, right. So, we are saying that because we are wanting to find the transition probability from I to j, where j is an absorbing state, and for the first time. So, first passage time you are computing mean first passage time. So, this will be that you transition from I to another transient state, then from that transient state your absorbing probability. So, a k j into m k j. So, the mean number of transitions that you will require for going from k to j m k j. So, this gives you an equation for relating the m I j's with the other mean first passage times to the absorbing state j. This is the right. So, if passage to state j is certain to occur, then of course, a k j will be 1, and in fact, all a I j's where j is fixed will be 1. So, in that case, you see these equations will transform to, because this will be 1, this is 1 and this is 1. So, then if you recall your equations for m I j's which you wrote down for the ergodic process, you will get the same equation mean first passage time, right. That means, now you are considering that there is only one absorbing state, and so the mean first passage time equations will be valid here. Okay. So, the whole idea is when you have more than one absorbing state, you want to look at the, you want to see the how to compute these mean conditional mean first passage times. So, let us say that you now in the example that we have been all along following, the fourth state example, in which 1 and 2 are transient and 3 and 4 are absorbing. So, you consider the state 4 state, which is okay, and you want to compute m to 4. That means, you are in 2 and you want to find out the mean first passage time of going to 4, to absorbing state 4. Okay. So, here if you look at this equation, let us just write it out. So, it will be a to 4 m to 4. So, now 2 cannot be equal to so when we will now make use of the conditional mean first passage time. So, I am defining m I j as conditional mean first passage time from I to j. Okay. And okay, I am defining the conditional mean first passage time. This may be a general definition, but in particular now I want to say that suppose j is an absorbing state, I want to talk about that only. Okay. So, in that case I can write this as a I j m I j, right, because the transition probability or the absorbing probability from I to j is a I j, and that into m I j the mean conditional mean first passage time. Then either this transition occurs in one step, or it will occur, that means you will go from I to k, where k. So, I need not write here, essentially I mean that k is a transient state, is a transient state. That is all I want to say. So, then this will be you may transition to another state or to itself p I k, then a k j. So, k cannot be j, that is all, because j is an absorbing state. So, once I transition to j, then it is done, I do not have to. So, it will be p I k, that means I transition to another transient state. From that transient state I go to the absorbing state j. So, the probability of that into the mean first passage time from k to j. Okay. So, k is a transient state. Okay. Now, if passage to state j is certain, then you all these absorbing probabilities are 1, right, because no matter where you are, since you know that you are going to go to j. So, all these probabilities will be 1, and in that case these equations will reduce to your computing the mean first passage times from an ergodic process, which we have done already. So, same equations, I mean this will reduce to the equations for computing the mean first passage times for an ergodic process, right. So, now let us see how we make use of these equations to compute your m I j's. So, let us consider, say for example, I want to compute m to 4. So, that means the question here that we asked, how many transitions will occur before the specified absorbing state is occupied. So, of course, I will compute M24 then M14 also, and the sum will tell me. So, that means your to answer that question, it will be M14 plus M24. That will tell me the mean number of transitions that are required before I occupy state 4. This is what we want to compute. Okay. So, let us just write down the equations here. So, A24 into M24, this can be equal to A24, which is actually 1 times A24 plus, then from 2 I can transition to 1, which is a transient state, then A14 into M14, or I can transition from 2 to 2. So, P to 2, then A24 and M24. So, this is clear, right. Similarly, if I want to look at M14, then it will be A14 into M14, then 1 into A14. So, I will again transition from 1 to 4, and this will be yeah. So, this will be in one step, and then I mean the mean first passage time will be 1 plus P11 A14 M14 plus P12 A24 and M24. Okay. So, here again from 1 you can transition to itself, or you can transition to 2. So, if you transition to 1, then again you want to compute A14, and then this will be M14 plus P12 into A24 M24. So, this is the conditional mean first passage times that we are computing, that if I am in 1, then I can transition to 4. So, what is the conditional probability, right. So, now substituting for Pij's, I should not say Pij's, substituting for Aij's. And so, remember we had for this thing we had computed the matrix A, and if you look back at the matrix A, it is the numbers are given to you. So, A14, for example, there A24 is 3 by 5, then this was 3 by 5 plus 1 by 3, this was 1, this was 1, A14 was 1 by 5, then 1 by 3 was P21. So, anyway you had the matrix this, and you had the matrix the transition matrix P, also the transition diagram. So, looking at those, if you can just revert back to a few frames earlier, then you have all these numbers, and so by substituting there I get these two equations, and then solving them easily gives me the answer that M24 is 93 by 45 and M14 is 153 by it should be 45 only. Why 43? Right. Okay. So, as I was saying that now if you want to look at the M14 plus M24, then this is equal to 93 plus 153 45, and this will be 6 45. So, on the average the mean number of conditional, that means if transitioning to 4. So, the number of transitions that will be required, a mean number would be 246 by 45, provided you are transitioning to the absorbing state 4. Okay. So, one can I have tried to look at these processes in different ways and given you interpretations, and so given a physical process, there are a lot of these kinds of questions, because you want to know if one has to plan, then one has to know, for example, if these are reducible Markov chains, that means which the processes which will terminate in short time, then you want to have an idea about these numbers, these, so that you can plan accordingly. And let us hope that in future, after having gone through this, you will be coming across such situations or such processes, where then you can look at them in a more meaningful way. Okay. So, I will now discuss exercise. So, let us look at question 1. This is a particle moves, by the way these questions I have taken from the book Hillier and Lieberman, reference to which will be given to you at the end of the course. So, a particle moves on a circle through points that have been marked 0, 1, 2, 3, 4 in a clockwise order. Okay. So, and the particle starts at point 0. So, let us see, I can just, so here is a circle, and you have 0, 1, 2, 3 and 4. So, this, and the idea is that you can either move from here to here or you can move backwards. So, at each step the particle starts at point 0, at each step it has probability 0.5 of moving the point clockwise. So, clockwise would mean this way, or 0.5 of moving one point counterclockwise, that means either backwards or forwards, and both the probabilities are the same. So, you remember this was your we were looking at the random walk. We were looking at the random walk, and when we said that probability is half, then we also showed that it will be an ergodic process, because in that case all the states will be recurrent, right. So, same situation. Now, let x n denote its location on the circle after step n. X n is a Markov chain. So, we have already seen that this will be a Markov chain, because it will just depend on where you are. So, that the probability of transitioning to the next step will just depend on where you are, it will not depend how you reach there. So, this will be a Markov chain. Now, construct the one step transition matrix, you can do it, right. So, it will be a 5 by 5 matrix. Then determine the n step transition matrix P n for n equal to 5, 10, 20, 40, 80. Now, I have given up to 80, but just because you can either, because you must be familiar with MATLAB, or by writing a small program of your own, then you can iteratively find out, multiply, get the power of p raised to 5, p raised to 10, p raised to 20 and so on. So, just to familiarize yourself. Then determine the steady state probabilities of the state of the Markov chain. Now, so okay, this is a little may become tedious, because you are solving a 5 by 5 the transition matrix is 5 by 5. So, you will have 5 variables and 5 equations, but since the values of p's are half, so therefore, it should not be a difficult system to solve, you should get the answer quickly, right. So, determine the steady state probabilities of the state of the Markov chain, describe how the probabilities in the n step transition matrices obtained in part B compared to these steady state probabilities and as n grows large. So, want to see that you should feel the, so once you find out the steady state probabilities, and you also have like p raised to 40 or 80, then you can see that in fact at p n equal to 80, that means when you have p 80, p raised to 80, then they should definitely be very, very close to your steady state probabilities, and in fact you can see the pattern even when you compute p 40. Okay. Now, question 2 is just to determine the period of each of the states in the Markov chain that has the So, here you have again a 5 by 5 matrix, and I am asking you to determine the period of each of the states in the Markov chain that has the following transition matrix. So, this will be all the states are periodic. Well, you find out. Okay. So, you have to then determine the period, that means you will have to compute p square, p cube, and so here also you can make use of the same program that you wrote for B, and then you can compute p square, p cube, and so determine the periods of the periodic states. Yeah. Now, question 3, a transition matrix P is said to be doubly stochastic if the sum over each column equals 1. So, for the transition matrix that we have seen, the rows must add up to 1. So, now I am giving you an additional condition, and that is that the columns also add up to 1. So, therefore, p I j as I varies from 0 to m is also 1, right. So, column sums are 1. In that case, such a chain is irreducible, aperiodic, and consists of m plus 1 states, right. The states are already m plus 1. Show that your steady state probabilities in such a case, you do not have to do any computations, just right away you will be able to show that your pi j's are 1 upon m plus 1 for j varying from 0 to m. Okay. So, this is simply, you can do it orally, but write down a few things and then make out your okay. So, this is now this is okay. Now, question 4, a computer is inspected at the end of every hour, it is found to be either working, which means up, or failed, down. If the computer is found to be up, the probability of its remaining up for the next hour is 0.9. If it is down, the computer is repaired, which may require more than 1 hour. Whenever the computer is down, regardless of how long it has been down, the probability of it still being down 1 hour later is 0.35. So, that means your unit of time is 1 hour, and then you have to write down your transition matrix. So, construct the one step transition matrix for this Markov chain, okay, and find the mu I j, the expected first passage time from state I to state j for all I n j. Okay. So, this you will be able to do. So, here I have asked you to now sort of, this question depends on computing the first passage times, which we have also discussed quite thoroughly. Okay. Now, the question 5, which I told you in the lecture is based on the gambler's ruin problem, and so I thought that I will leave the computations to you for I just explained to you how what the problem is. So, now here okay, gambler bets, there should have been a space between. So, now this is a gambler bets dollar, okay, here it is $1 on each play of a game, because this is again from Hillier and Lieberman. Each time he has a probability p of winning and probability p of winning and probability q, which is 1 minus p, of losing the dollar bet. He will continue to play until he goes broke or nets a fortune of $t. Now, let x n denote the number of dollars possessed by the gambler after the nth play of the game. Then you want to find out x n minus x n plus 1 will be x n plus 1 with probability p, right, because he has 1 more rupee if he wins, and that is with probability p. Otherwise, he will have x n minus 1 with probability q, which is 1 minus p. Now, here of course, he continues playing only if his x n is less than t, and x n plus 1 will be x n for x n 0 or t, right, because if he has no money, then he can't play, and therefore, he can't bet, and so he continues to be in the same state, that is means he continues to be broke. And if he has t dollars, he has earned t dollars, then again he does not play, because he has earned his fortune. Okay. Now, x n is a Markov chain, we have already discussed this. The gambler starts with x naught dollars, where x naught is a positive integer less than t. So, as I said, you can say that x naught is I. Construct the one step transition matrix of the Markov chain. So, this you will have to write down, right, and you can see that it will only be one step forward or one step backward, the other entries will be zeros. Now, find the classes of the Markov chain, these I have already told you. Let t equal to 3 and p equal to 0.3. So, if it is a question of earning up to $3. So, that means your states will be 0, 1, 2 and 3. So, then I have asked you to find out the first passage probabilities f10, f1t, f20 and f2t, and then again the same things when p is 0.7. So, it will be not difficult at all if you write down. See, again the computations, the formulas are given to you for the first passage probabilities, and so once you write down the transition matrix, you should be able to complete the problem. Okay. So, in the lecture I had told you that I will be asking you to compute the probability that the gambler will end up with rupees t, or in the lecture it was I think rupees n or dollars n, whatever it is, does not matter. That means the gambler with what is the probability that he will earn the fortune that he is wanting to. So, that has not been asked in this question 5, but you see you should be able to set up equations. So, essentially it is just define the probability pi minus 1. So, you can interpret the same way, and then it will be pi is equal to pi plus 1 plus q pi minus 1, and then you multiply pi by p plus q, because p plus q is 1, and then from this equation you have an iterative relationship for different values of I, and then you can find out the iterative relation, and then you will be able to find out the probability pi. And there of course, you will use the fact that if you have $0, then the probability of making your fortune is 0, and if you have earned $t, then your pt is 1. So, using these initial and boundary conditions, you will be able to solve for PIs. So, please do that, because in the problem I have not asked you to do it, but you can certainly do it. Okay. Now, question 6. Question 6 is which is again a simple one. A leading brewery on the west coast labeled A has hired an OR analyst to analyze its market position. If it is particularly concerned about its major competitor, let us say labeled B. So, another brewery which is the competitor for this brewery A, and so they want to find out how good a competitor or how bad a competitor this other brewery is. So, the analyst believes that brand switching can be modeled as a Markov chain using 3 states, with state A and B representing customers drinking beer produced from the aforementioned breweries, and state C representing all other brands. Okay. So, state A will represent, so that means A to A in this the transition matrix that was given below. So, say probability of A, that means somebody who is using the beer from brewery A will continue to do that, use the brewery A only is 0.7, but may switch to B with probability 0.2 or to other brands with probability 0.1. Similarly, you can explain the row B entries, right, and then C. For other brands, then they switch to A will be 0.1 and 0.2, 0.1 again to B, and 0.8. That means they continue with the same brand that they are already using is 0.8. So, that point is missing here. Anyway, just you can make the entry. So, 0.8, right. Now, what are the steady state market shares for the 2 major breweries? So, we want you to find out pi 1, pi 2 and pi 3. So, the answers that they are asking for is pi 1 and pi 2. So, what are the steady state market shares for the 2 major? That means, when the process has gone on for some time, you think that the choices have all stabilized, then you want to know the steady state market shares for the 2 major breweries.